My name is Hui Cao. I'm from Yale University. I'm a physicist and also engineer who has been, I've been developing lasers for different applications. So today I'm going to talk about this violin laser. You may ask me, what's the relation between a violin and a laser? So I think some of you play violin, so you know that basically for violin, we actually have this kind of, like a wooden body, have this kind of shape. So what it does is that this kind of a hollow wooden body will resonate with the sound that is generated by the string, and then it can amplify it. Okay, so the reason this body is made this kind of very strange hourglass-like shape is because for this kind of shape, it can really resonate with sounds of different frequencies or different pitches, right? So that will make the violin sound rich. So in other words, this kind of wooden body serve as a resonator for the sound. So this is for violin. So now let's see what happens to a laser. Actually, here for a laser, we have actually a gain medium that you can think about like a string that can generate light. And then we also have a cavity. Here shows this shape like an hourglass. That's actually this cavity is try to resonate with the light that's generated by the gain medium. So it really function as a resonator for the optical waves, just like this violin wooden body serve as a resonator for acoustic waves. So then we try to design the cavity shape in also similar to the violin so that they can resonate with optical waves with many different frequencies. So then all these different waves, they can interfere with each other. So when they interfere with each other, they can generate very rapid and random intensity fluctuations. And those fluctuations is on the time scale of 1 picosecond, that is 10 to minus 12 seconds. So this kind of very fast, random intensity, fluctuation can be digitized to generate random numbers. And because this intensity fluctuation at the different spatial locations are different, so they can generate many different random bit streams in parallel. So here we are actually using this to make a parallel ultrafast random number generator using this kind of single laser chip of size less than 1 millimeter. And we can have like a 127 independent channels. Each channel can generate a random bit at the rate of 2 terabit per second. Terabit, what is 10 to the 12 bits, okay? And then, so in total, we have 254 terabits per second. That is 100 times faster than the existing state of art. So then you say, what is the use of random numbers? Random numbers has been widely used in our daily life for cybersecurity, for secure information. And these days, actually, we are more and more rely on the random numbers for secure online banking or online purchase. So the commonly used random number, they are generated by computers with some deterministic algorithm. So they are not true random numbers, but pseudo random numbers. So therefore, they are valuable to attacks. So true random numbers can only generate by physical process, like the laser chip I just showed you. And the ability to generate a larger number of random numbers at a very high speed will be very useful, and also is becoming increasingly important for all these online activities. But besides this, cybersecurity, actually, this high quality random numbers will also be very useful for stochastic modeling and also for quantum simulation. For example, to simulate the spread of disease, and also for yes, I got it. Thank you. And also for stock market, fluctuations. So therefore, we basically show that we can using a single laser, chip, which is similar to the violin, shape to really generate huge number of random numbers. So with that, I'll stop here. I'd like to thank to all my colleagues and collaborators that have contributed to this work, and also the funding agency. Thank you for your attention.